Okay, so for problem number 4 on the 2015 exam, they're really after just, do you know what's going on molecular speaking? So it says, based on the data in the table they gave you, what type of intermolecular forces? I said London dispersion forces, and as you see the polarization increase, so does the boiling point. Again, the more polarized that you have, the stronger intermolecular forces, and that's kind of what they're after. Talking about London dispersion forces, intermolecular forces, those sorts of things. And part B, based on the data in the table, the student predicts the boiling point of HF to be 174 Kelvin. The observed boiling point is 293. Explain the failure of the student's prediction. And I simply said that the HF must have more hydrogen bonding. Thus, that would lead to even a higher boiling point. Hydrogen bonding is much stronger than London dispersion forces. So that's kind of the way I put it. They put London dispersion forces and hydrogen bonding. Hydrogen bonding is much higher, therefore that explains for it's much higher. The representation of the 5 molecules in HBr in the liquid state is shown in box 1, and box 2 draws a representation of 5 molecules after vaporization has occurred. And what I did was make sure that I showed 5 molecules, and I just scattered them all over the box. And anything like that is fine. Just showing them scattered all over the box, showing that kind of representation. Okay, so problem 4 is not too bad if you get, again, talking about London dispersion forces. Okay, problem 5, you have a molecule, ethanoic acid, and it says the molecular formula for the compound is C2H4. Draw a complete lowest structure of the methylmethanoate in the box below and show all valence electrons. I did it 2 ways. I showed them with all valence electrons and showing all bonds, or I'm going to show it like this, but please, if you do this, you've got to show the unshared pair on the oxygen. It's important. See, all 4 of carbons is being used up here, so there's no leftover. Same for hydrogen, same for that carbon. Oxygen has unshared pairs, so you've got to make sure you show those valence electrons, since that's what it's asking you to do. Okay, in part B, it says, assume when the equilibrium is reached 50%, reached 50 has been reached 50%. The ethanoic molecules has been reached. Oh, I'm sorry. They give you some information above, and then what's it asking you? Part I says calculate total pressure of the molecule. Let's grab the different colored pen here. That's okay. PV equals nRT, and I'm after pressure, so it equals nRT over volume. I've got 0.015 moles. R, of course, is 0.08206 liter atmosphere moles Kelvin. And I am told I've got a 1 liter vessel. And the temperature, I've lost my place here, is 450 Kelvin. And when I solved that, I got 0.55 ATM. Again, I apologize for stretching all the way across. It makes it harder for you to see. Now, part 2 says calculate the value of the equilibrium constant at those particular situations, and got all of it. Yeah. And part 2 is a little bit harder problem because it's talking about talking about. I'm sorry, I got 0.56 here. My bad. I was looking down at something else. Now I'm confused. No, I did get 0.55. I apologize. They got 2 different ways of doing this problem, and I looked at theirs instead of mine. So I apologize again. 0.55. That's a 5. Golly. I don't want to do the video over 5 ATM. All right. Then it says to calculate the value of the equilibrium constant for the reaction 450. And I looked at the mole fraction from that reaction because you go back to that part. It says assume that when the equilibrium is in, 50% of the ethanoic molecules have reacted. And so I basically said that the product is 1/3 the total. So I said that the product is 1/3 the total times 0.55 atmospheres. And therefore the reactants is 2/3 times 0.55 atmospheres. And then I said that Kp equals the product, pressure of the product, over the pressure of the reactant, and you got two of those, so that is obviously squared. And then I put 0.183 for the product, and that was 0.367, and I've got to square that, and that gave me 1.36, and there's two significant digits, so 1.4 is the answer I get for that. And I know that's a hard problem because we got 0.015 total moles. We're told half of it is used up. And so we already calculated the pressure is 0.55 atmosphere. And again, the products are going to be 1/3. Half of it's gone. So it's going to be 1/3 because you have a 2-to-1 ratio. So that's what you got to keep in mind. And then, that's the way I did it. Looking at their answers, they got they had 0.56 they used earlier. They had 0.39, 0.19, 0.37, excuse me, 0.19. Still gives us 1.4 in the ratio. So I hope that helps. That's a harder problem, but I just use the gas loss for it.